Let's wait for a couple of minutes. Let's wait for a couple of minutes. Right. Am I audible to everyone? And the presentation is visible to everyone?
Yes, sir.
Oh, okay. Good. Um, yeah. So today's discussion will be on linear approximation and critical points of a multivariable function. All right. So we have already seen what are multivariable function. We have also seen the partial derivative of the functions, how to compute the limits of multivariable function, and as well as we have also seen, we have also defined gradient of the multivariable function as well as the directional derivative. Okay, so let me quickly write down all those details. So, let f be a function defined on a domain sitting inside Rn to R. So f is a scalar valued function defined on a domain in Rn, and we have seen uh, right. So we have already seen how to define the limit of a function, limit of a limit of f. Okay, we have also seen the partial derivative. The partial derivatives are nothing but the differentiation of f along the direction of the coordinates, the coordinate vectors. Okay, unit coordinate vectors. So, for example, if I have a two variable function, then I will be differentiating with respect to x and y. So, fx is defined to be the limit of h tends to 0, f of x plus h comma y minus f of x comma y divided by h. And similarly, f of y is defined to be the limit of function f in the direction of coordinate y. All right. So this is for a function defined function on a two variable. Similarly, one can generalize these things. So if my function is defined on a domain inside Rn and it's a real valued function, then I will have partial derivatives, which will be uh, so at So at a point a tilde, which is nothing but a up to an, a vector in Rn, the partial derivative will be defined as x1, f of x1, f of x2, f2, so on, f of x. Okay. This and we have also seen directional derivative. So in terms of directional derivative, these partial derivatives becomes the directional derivative in the direction of the unit coordinate vectors. All right. So we have seen that given a function f from Rn to R, yeah, is there any question, doubt, suggestion, comment? All right. So directional derivative of a multivariable of a real valued multivariable function uh, at a point A in Rn or inside the domain D in the direction of vector u, which is given by u1 up to un, is equal to the limit of the one variable function, okay, in the defined in the direction of u. So in particular, f of u at a tilde is the limit of h tends to 0, f of a tilde plus h u tilde minus f of a tilde plus divided by h. All right. So this is what the directional derivative is. And as you can notice here that the term inside this term, this is a line. This is the equation of a line. So let me write it here. Is that this is the equation of a line. Equation of a line that passes through passing a tilde and passing this and in the direction of u tilde. All right. So if you look at your function f, so now f becomes, and there are, so f becomes a function of one variable because u tilde and a tilde, they are all constants. Okay, they are fixed values. They are not varying. All right. So they become a constant. Okay. So they are constant. These are constants. So your f becomes just a function of, so this is is a function of h. So h is the only variable. So it becomes a function of h. All right. So this derivative becomes a one variable derivative. Okay, derivative of uh yeah, so it becomes a one variable derivation. And we already know how to compute limits in one variable. So this definition is simple enough. All right. We at the end of the last session, yeah, we have also seen that uh, yeah. So we have also seen the relation between how to how one can interpret a directional derivative in terms of gradient. We have also seen that. So before that, let me introduce what is a gradient. So gradient of f at a point a tilde is the partial derivative of f at a, partial derivative of f uh, is the is a vector, is basically the direction, is basically the vector given by the partial derivative of f with respect to each of the coordinates. All right. And we have also seen that if this exists and it is continuous, is this gradient is continuous near a ball, continuous in a ball containing a tilt, then the directional derivative can be expressed in terms of the gradient. So directional derivative fu at a tilt is nothing but gradient of f at a tilt dot product with vector u. Okay. This is also uh, you guys have seen in the at the end of the last session. At the end of the last session. So this is the gradient. Okay. So I will start my today's discussion with this last equation. Okay, where we have expressed our directional derivative in terms of the gradient and dot product of gradient with the direction. All right. So now we want to find out. Uh, yeah. So we want to find out in which direction we have the steepest descent or ascent. All right. Now, what does it mean to find out the direction in which the steepest ascent or descent makes sense? So think of it as you are on surface of a mountain or on surface of a on top of the hill, and then you pour some water from that, and then the steepest descent will have the fastest speed of the water flowing down. All right. Uh, Similarly, the steepest ascent will be the hardest part to uh, climb up the mountain. All right. So now, which is uh, which direction is the steepest ascent and descent is? So directions of steepest ascent and descent that can be calculated using this formula. Okay. So in particular, the steepest ascent is where the function, the directional derivative, is the direction where the directional derivative takes the maximum. Okay. And steepest descent is the direction where the directional derivative takes the minimum. All right. So, yeah. So let me write down directions of steepest descent and ascent. All right. So steepest descent is where, suppose this is, so which direction has the steepest descent and which direction has the steepest ascent and which direction uh, the directional derivative remains zero. That means your function doesn't vary along that direction. So there are three directions involved. One direction where you can achieve the steepest descent, other direction where you can achieve the steepest ascent, and the one another direction is the one where the function doesn't change. Okay, and so how to say these things in terms of the directional derivative? So the direction where your directional derivative achieves the maximum is called the ascent. So along the steepest ascent, the directional derivative attains maximum. All right. So how to see if I use this formula, u tilt. So u tilt. And now what is the dot product? So if I write down the dot product, this dot product is nothing but the norm of the gradient times the norm of the direction times the angle between the gradient and the unit direction of uh, the unit direction of vector u. All right. So I'm taking the unit directional derivative in case it is not clear from the context, because last time we also discussed the same for the unit direction. So we are taking for the unit directional derivative, right? And then if you solve, now when does cos theta achieve its maximum? What's the maximum value of cos theta?
Theta equals 0 when both are
Theta,
along each other.
right. So theta equal to 0 is the when is the direction. Yeah. So cos theta. So we know that we are working with a unit direction. So u is 1 and cos 0 is 1. So that's that's when we achieve the maximum. The directional derivative is maximum. So that's what is the. So there is a mic on. If there is a, can you please? Someone's mic is on.
I'm this Sadik. Your mic is on.
Yeah. Okay, that's better. So cos 0 is equal to 1, right? Uh, all right. So now f u tilde a tilde. So what is the direction? Direction is precisely uh, yeah. So what is the value? Value is precisely uh, gradient, the norm of the gradient. Okay. And similarly, so what will be direction? So direction will be, yeah. Similarly, if uh, so, what do we understand from this is that the direction of the directional derivative, sorry, the gradient direction. Let's say this is the gradient direction, and the direction of the directional derivative, they are in the same direction. So unit direction vector is also in this direction. All right. For the steepest ascent. Now for the steepest descent, the unit directional derivative attain minimum. And when does that happen? When cos theta takes the minimum value. And what's what is that angle for cos theta to take minimum value?
It's pi.
So Yeah. So for theta equal to 5, cos theta is -1. And that's when you achieve the minimum value of this. So which will be minus, right, is u under over t, minus of the gradient, norm of the gradient. All right. So if I try drawing it down, then this is the gradient. Then the unit vector is this. All right. So for the steepest descent, and for the and for the vector, for the function being constant along that direction. That means if I look at the direction, if I look at the directional derivative in that direction, it should not change. So that means it should be 0. So along the direction, when uh, when function stays constant, so in that direction, uh, we have fu to be 0. Okay. So what would be the cos theta? So cos theta, so it is norm of fu cos theta. So this would imply that theta has to be pi by 2. So that means the direction has to be perpendicular to the gradient, like this. All right. So now I can write down it as simply that the steepest ascent is when fu is max and is positive as well, and the direction is, so this is the direction. I will write down the direction in this way. So direction is direction of the gradient. So because it's a unit direction, so I will divide it by the gradient norm of it. All right. So it is all at k tilde. All right. And for the steepest descent, we all know the direction is going to be a negative of this because it's in the opposite direction of the gradient. All right. And the constant. So in this case, fu is equal to 0 and the direction is perpendicular to the gradient. All right. So now let's discuss an example where we need to find out where we have a given a multivariable two variable function, and then we need to find out descent direction, steepest descent direction, or steepest ascent direction. Okay, there can be questions where you have given a steepest uh, descent direction, and then you need to figure out the other details. Okay, so I will not. Yeah. So first, let us discuss that one example, and if time permits, or maybe in the next session, I will discuss more of those different type of examples. So let's say this is a two variable function. At pi comma 1, find out the direction of the descent, direction of steepest descent. So since it's the descent, it will be negative of the gradient divided by the norm of this. And so what do we need to find out? We need to find out the gradient of the function and its norm. So what is the gradient of this function? So first let us find out the gradient and then we will evaluate at a tilde. So what is the gradient of this function? It is fx fy. Now what is fx fy?
Y cos xy and x cos xy.
Correct. And if after evaluating it to pi comma 1, we get cos pi, uh, sorry, yeah, it is 1 times cos pi and then pi times cos pi. All right. Now, what is cos pi?
It's minus 1 and
Right.
minus 1 comma pi.
So it is
Minus 1 comma minus
minus
pi.
1 comma minus pi. Right. That's the uh, answer. And now the norm of this is 1 plus pi square root of that. So the steepest descent is steepest direction of steepest descent is equal to minus of this, which is going to be 1 by pi divided by 1 plus pi square. All right. So this is quite a standard question. It's just computation. There is nothing involved in this. Okay. All right. So by this, why steepest descent and steepest ascent directions are important? Because these are some useful facts that help us to understand the uh, nature of the function. Okay. All right. So as we have discussed, so we already know one variable calculus, one variable differentiability, all these things. And in one variable calculus, one of the property that you have seen is the tangents to the tangent lines to the graph of the one variable function. So let me recall that first. And the similar kind of construction we want to do for multivariable. Okay, so we have also seen linear approximation, approximating a function by a linear function uh, at at some point. Okay, to get better approximation of the function values. So similarly, we will try to do in the case of uh, multivariable as well. Uh, and for that, we need to first know what is a uh, tangent space or tangent plane in this in the multivariable or tangent hyperplanes in multivariable case. And okay, so let me just start with discussing the one variable case, which you guys have already familiar with. So suppose, so this is my one variable column. Okay, so all right, this is my one variable column. On the right, I will draw the multivariable two variable column. So in one variable, we have let's say we have a function f defined on some domain r to r. So let's take the domain to be let's say minus 2 to r, and let's say my function is basically x going to my function is defined to be fx is equal to, let's say, sine x. All right, better to take the domain to be minus pi to 5. Okay, this looks better. Okay, so suppose this is my function sine x. So now if I draw the graph of this, so what is the graph of f? So graph of f is graph of f is a function is the domain comma the value of function. Okay. Domain point comma the uh, second coordinate is the value of the function. So it is always part of domain cross r. Okay. So domain cross the range. In our case, the range is r, and we only be working with scalar valued function. So it will, in our case, it will be fixed to r. So uh, yeah. So the graph of function is a subset of this Cartesian product space D cross R, where D is the domain and R is the range. Okay. All right. So this is the definition of the graph. of function. So now if I draw the graph of this function, so it will be drawn. So it is a domain from interval times r. So it will be drawn on R2. So my graph of this space sits inside minus pi to pi times r, which is a subset of R2. So I will be drawing this on R2. All right, that makes sense, right, to everyone? Is there any question to that? So the graph will be part of R2 thing. So my x-axis is x-axis and my y-axis is f(x)-axis. All right, now we draw the graph of this. So the graph will look like, so it will hit -1, and then it will hit +1, and then it goes to 0. All right, this is my graph. All right. So now, if I try to look at this point, so let's say this is my point A, and if I try to approximate this point function at this point, which in particular in nearby this point, then we need to, by a linear function, then the best approximation is the line that touches at this point and passes through, that touches the line that only touches at this point, and it is tangent to this point, to the graph of this function. Okay, so that's why it is called the tangent line. So this is the tangent line. Okay, tangent line at A in domain. All right. Now, how to find out the equation of this tangent line? That is one thing that you learn in one variable calculus, to find out the equation of the tangent line. Because once you know the equation of the tangent line, you know the linear approximation as well. Because that equation of tangent line will be the linear approximation of the function near that point. Okay, and why linear approximations are important? Linear approximations are important for numerical purposes. Okay, to find out the nearby values of the function, because sometimes it is difficult to know the exact value of the function. So linear approximations are good in that. So how to find out the equation of this tangent line? Yeah, you guys can participate because it is one variable calculator on the call.
So we can use the 2-point slope form, which would be if it passes through points x0, y0. So we can
Right.
have the equation of the straight line as y minus y0 by x minus x0, which is equal to dy dx, that's f prime of x. Let's say it's x prime of x,
So
f prime of x.
this is what
Yeah.
you were referring to,
Yeah,
right?
yeah, right. The 2 points.
So for this, we need 2 points, right? We need 2 points to know. Do we know 2 points in this graph? Do we know 2 points? Let me just try to.
Yeah, but what we can do is that this m, the slope of the line, we can compute as dy by dx. That would be f prime of x at
Right,
x.
right. So that is what? That is the gradient in one variable, right? So you have correctly pointed out that we can, so this part of the equation, which is the slope, is the slope. All right. So this part of the equation, which is the slope, this can be calculated. So the slope m can be calculated by df by dx evaluated at x equal to a. Okay. So this is this can also be think as f prime of a. Right? This is f prime of a. This is nothing but the f prime of a. So if I place this into this, and now what is my, and do we know any point that it passes through? Do we know any point
So
that it
yes,
passes through?
0,
Yeah.
0.
it's
It's passing
it passes
through.
through x comma 0 and y comma 0. 0 comma y.
0, 1.
No, x comma 0.
This
Uh,
curve passes through origin, right?
yeah. No, this is very specific curve. but try to think of in generality. If you don't know the function, for example, you don't know this is a sine function, okay, and you have some random graph given, then in that case, uh, you only know this point. Which what is that point? At the point that you are calculating the tangent. So you know this point. Now what is this point? This point is a comma f of a. So this point you always know. In this case, you know multiple points, so you don't need to worry about. But you are calculating at but you are calculating tangent at a comma 0. Sorry, at a. So the only point that the tangent line hits is a comma f of a. It doesn't hit x comma 0. It doesn't hit origin. Okay. So whatever you were suggesting was not the uh, correct points. So it only hits this point a comma f. So we have two informations. We have so my x naught y naught is a comma f a and this. So now I know the equation of this tangent line. All right. So now what will be the equation? Equation will be
y minus f of a by x minus a equal to f dash of a
yes, y minus f of a is equal to f prime of a
into
x minus a, right? And now this is nothing but f prime of a x minus a plus f of a. So this is called the linear approximation of uh, function f at a. Okay, this is a one variable linear approximation. All right. So now, if I want to write down the parametric equation of this function, okay, if I want to write down the parametric equation of uh, yeah, parametric equation of this line, tangent line, okay, in terms of parameters. So parametric equation of the tangent line that passes through a comma f a and in the direction of in the direction of what? So so in this case, we need to uh, find out the direction. So what is this? So we need to find out this vector. What is this vector in R2? Okay. So this vector must be having some coordinates in terms of R2. Can we find out that coordinates? Yes, we can find out. And the way to find out is because this is a graph. So this is nothing but the tangent to the graph. This is nothing but the derivative of the graph. This vector is the derivative vector. So if I just calculate, so my graph of the function is graph of graph of f at x is x comma fx. So if I look at the derivative of this, then it is 1 comma derivative of f at this, then it is 1 comma this. So this will be my direction. So this is my direction of the function. So in the direction of 1 comma f prime a. Now, what is the parametric equation of a line which passes through a point and in the direction of that? You just need to add these two things up. So our vector r is given by the point that it passes through plus t times the direction. Okay, so what it will be? It will be a plus t f of a plus t times f prime of a. Now what is r? R is my x comma y. All right. So this is the parametric equation of the line. And the above one was the equation of a line uh, as a graph as a function of x. Okay. This is the parametric equation of a line, tangent line. Now, similarly, I want to repeat the same procedure in the case of, let's say, two variable. So in two variable, let's see what happens, what changes, and what kind of things we can generalize. So again, I start with a function f, which is on a domain sitting inside R2 to R. So it's a real valued function like the one we have started with. So in this case, I have very specific function, but let's not take any specific function. In this case, again, the definition of graph makes sense. So let me put it in the center. So graph of the function remain as it is. And now, in my case, the graph is a subset of D cross R, which is a subset of R2 cross R, or in other words, R3. Okay. So it's a subset of R. Now, in this case, it will be a bit harder for me to draw the graph, but let me try. So yeah, let's take this thing and then try to okay. Try to think of it as some yeah, it looks like a graph of something. Uh, so this is my this x-axis is y-axis and this is f of x y-axis. Okay. So this is a 3D figure that you guys see. We should. This is the bottom, and the rest is the it's like a head that is placed, uh, that is defined. It takes a value from in some certain discount. So this is this figure does this figure make sense to you? All right. So now in this figure, I want to find out the approximation or tangent to this point. Let's say, let's take a point here. Let's take a point here. Okay. Call that point to be A comma B. And then if you look at the image of this, so it will give you a point A comma B comma f of A comma B. Okay. On the graph. So this will give you this point on the graph. All right. And now, suppose you also have a direction. So in this case, we only had one direction, there was only one direction, which was this direction. So in this case, so you have taken that direction there, but in this case, there are infinite possibilities of direction. So let's take this unit direction, u, along which you will perform the directional derivative. So you perform directional derivative along this direction in the xy plane, and it leads to a line which is tangent to this point in the direction of this, to the one variable function that you have along this direction. All right. So let's say this is the one variable function that will form, and it will take the values. Just taking different. And then it goes here. So this green line that you see is the graph of this one variable function. Okay, let me zoom in if this picture is not. All right. Right. So I have taken this direction u in the xy plane. And if I restrict my function in this direction, that means uh, if I restrict my function, if I just take my function on this line, okay, which is u, what is this line? This line is a comma b plus tu. Okay, if I restrict my function onto this line, then this is a one variable function in terms of t. All right, as we saw earlier in the definition of directional derivative. And the graph of this one variable function is precisely this green line. Okay, so does that make sense to everyone? Now this becomes a one variable. It becomes a case like one variable. Okay. Now you need to find out the tangent line to uh, this green graph. Okay. Now what is the tangent line to this green graph? So let me copy this picture because it looks too messy here. Let me copy this and then paste it somewhere else, and then I will discuss more on this. All right. So the picture is here. Right. This is what my picture looks like. So let me draw this thing. Right. So that's my f of xy, and this is my this is y axis on this. Now the direction of this point, uh, yeah. So this will be the tangent L. This will be the tangent line at this point to the graph uh, of yellow. So at this point in the direction of u, the tangent line is this. So let me use LU because it is corresponding to the direction u. All right. So now, what will be the equation in this case? So again, we need to know the direction to find out the. So we need two things to find out the equation of tangent line. I'm talking about the parametric equation. So we need two things. One is the direction, and other is the point that it passes through. So we already know that it passes through a comma b comma f of ab. Okay. So clearly line LU passes through the point uh, a comma b comma f of ab. All right. Now what is the direction? Direction is this direction u and the direction of the gradient. Sorry, the direction of u and the direction of the directional derivative of f. Okay. So and the direction is f is the vector u and f u at a comma b. Okay. So let's take u is a two coordinate vector. So it is, let's say coordinates are u1 u2. So it is u1 u2 f of u a comma b. Okay, this will be the direction. And now once you know the direction and the point it passes through, we know the equation of the tangent. So the equation of tangent line, thus the equation of tangent line is it is x y z equal to x y z equal to a b f of a b plus t. So it is similar to the one that we had in the case of two variables. T times u1 u2 f of util at ab. All right. So yeah. So this will be function of the line. Okay.
So why
So
is it in the second term? So why is it t
uh,
times a1 u2 is u2 here? Okay, so u2 is okay. It's the y coordinate of the u.
sorry. Is there
So
any?
it should, yeah. So it should have been u1 u2, right? Yeah.
It is U1 U2. Yeah. Yeah. It might have looked A1, right? That was a typing error.
Yeah.
So it was, yeah, it was a writing error. So it is U1 U2. All right. So this makes sense, right? So we have generalized the concept of one variable to two variables. Now, and the idea is similar. Okay. So you look at the function. So this is the graph of the function in R3, and then you look at the direction, in which direction it becomes, in that direction, the function becomes a one variable function. And when it becomes one variable, we can talk about its tangent line. So we talk about its tangent line now, but this tangent line lives inside R3. So it needs to have the parametric form or the equation must be in R3 according to R3. So that's what, and any line can be described by just two things. One is the line, one is the point that it passes through, and other is the direction. So point we already know, and the direction we also know, which is direction u, and the other direction in the directional derivative. So the third coordinate comes from the directional derivative. So now we know that it gives you the direction, and once we know the direction and the point that it passes through, we get the parametric equation of the tangent. All right. Now from this parametric equation, one can obtain other type of version of it. For example, uh, one can write everything in terms of t. So, for example, if you compare coordinate wise, then you will get x minus a by u1 is equal to y minus p by u2, which is equal to z minus fu, z minus f ab by fu at ab. All right. So this, yeah, so you can, by equating t, you will get this expression as well. All right. So let me give you an example first because it has been too much theory. So let me discuss an example um, before we move into defining the higher dimensional version, higher dimensional tangent line equation for, yeah, before we discuss the higher dimension version of this thing. All right. So consider this example of two variable function x square plus y. Find out the line tangent at 1 comma 1 in the direction of 1 by square root 2 comma 1 by square root 2. Okay. So in order to find out the direction, in order to find out the tangent at 1 comma 1 in the direction of 1 by root 2 comma 1 by root 2, first we need to find out the direction vector. So the directional, so first we need to find out the tangent passes through which point, and the second thing is the direction. Okay. So, or we can just directly use the above formula. It will be easier. So xyz is equal to, so line of equation xyz is equal to a comma b comma f of ab plus t u1 u2 f of uab. All right. Now a is 1, b is 1, f of ab is 2t. u1 is 1 by root 2, u2 is 1 by root 2. Now what is fu? So let's calculate fu. What is fu?
is 2x
Now
to
for f,
y.
We have to take
yeah, for
gradient dot product with
mm, gradient, right? So let's do that. So if we take the gradient with the dot product with gradient, so what is the gradient? Gradient is 2x
2x,
comma
y.
y, but we need to evaluate it at 1 comma 1. All right. So if I evaluate it at 1 comma 1, then I need to dot product with vector u. So what will I get is 2 comma 2 dot with this, which will give you root 2 comma root 2. All right. So this is at 1 comma. Now place it back. What we will get, sorry, uh, it is a dot product. So so we will get
2, 2.
yeah 2 root. All right. So now the answer will be 1 plus t by root 2, 1 plus t by root 2, 2 plus 2 plus 2 root 2 t. Okay. So this will be the parametric equation of the tangent at this point in the direction of this vector of this function. Okay. Make sense to everyone? Good. All right. So now if I write down this vector, so if I write down this equation of line in, let's say, in another form, so let me so let me know if you find any difficulty in that. So xyz is equal to a comma b. Now a comma b, it is the vector. It is the point in the domain. So I can write it as a tilde. Okay. So thinking that a tilde is a comma b, I can write it like this, and I can write it like this. F of a tilde plus t. Similarly, u1, u2 is the vector u, and the directional derivative can be written like this. Okay. So it becomes the expression becomes this. Okay. On the left hand side, let me write the vector x2. Okay. So now the same expression, this is whatever we have proven for 2 dimension, the same expression can be generalized for any n-dimensional function defined on n-dimension, and the expression remain as it is. Okay. So it is directly coming from the two variable expression. It is the generalization of the two variable expression. So let me write down uh, tangents to a scalar valued function. So let f be a function on a domain in Rn, and it's a scalar value function. And let a tilde, which is a1 up to an, is a point in D. Suppose u is the suppose to be now fu at a tilde denotes the directional derivative of f at a tilde in the direction of u tilde, which is u1 up to u1. All right. Then the equation of tangent uh, the equation of tangent at a tilde is given by a tilde plus a tilde comma f of a tilde, your x vector on the left hand side plus t times u tilde plus f. All right. And if gradient f exists in continuous near a continuous near a
So it's u tilde comma
yeah,
f of u a tilde, right? Is it plus or comma?
right. It's a comma. Sorry. Then one can also write down directional derivative in terms of the uh, dot product with the gradient. Okay. So it is a perfect generalization of two variable, one variable case to two variable, and then from two variable to the multivariable. Okay. To n variable. So I don't think there is any confusion. There is any scope of confusion in this case. But still, any one of you have any doubt, you may ask. Okay, good. So when I was discussing the one variable case, I also wrote the expression for the linear approximation of the function. Okay, so this is precisely the linear approximation of f at x equal to a. All right. So similarly, one can have the linear approximation for in higher dimension. So in the place where we have the first derivative, in the place of this first derivative, we will have the gradient. It will replace with the gradient of the function, like as you may expect. And this normal product, this product, this scalar product, turn out to be the dot product in the case of higher, yeah, in the case of higher dimension. So let me write down the linear approximation as well, because you are already familiar. We have already recalled the one variable linear approximation. So let me just write down the formula. So let me first write it here. This is also all right. Okay. So now let me write down the linear approximation. of a scalar valued function. Okay, so again, suppose f is a function on a domain in R n to R. The linear approximation let f be a function in this such that the directional derivative of f exists and exists uh, f a tilde in D, and it is continuous as well, continuous on a small ball around a tilde in D, then the linear approximation is defined as f of Lx, the linear approximation of f near in the neighborhood of x, given by f of a tilde plus the gradient dot product with x tilde minus a. All right. So let us see some example of this. For example, let's say you have a function from R3 to R given by f of x, y, z equal to xy plus yz. So linear approximation find out the linear approximation of f at 1, 1, 0. So yeah, so for that, what will be the linear approximation of f? So what is f of a first of all? F of 1, 1, 1, 0. What is this value?
1.
It is 1, right? Now what is the gradient of f? Gradient of f is
Y, comma, X
yeah,
plus Z, comma,
right,
Y.
correct. And if I evaluate my gradient at, so this gradient looks continuous, right? This is a continuous function, so I can have this approximation. Now evaluating this value, I will obtain 1, 1, 1, right? So the approximation, so let me write down a small ball B around this. So this approximation makes sense for all x coming from that B intersection D, which is this part is important. It is not true for the whole domain. It's for the small ball near the small. Okay, yeah. So LFX, the linear approximation, is equal to, you just use the formula. It is 1 plus 1, 1, 1 dot product with x minus, so x1, x1 minus 1, x2 minus 1, or x3, or oh, we are using xyz.
It's right. 110, right? So it's correct.
Yeah. So then it will be x1 minus 1 plus x2 minus 1 plus x3 and plus 1. So it will be this. Okay. So this is the linear approximation of the function near point 110 for some small ball containing that point. Okay. Okay. So I have a question, another question. It is an exercise. If you are not able to solve it, we can discuss it on uh, Thursday. Suppose suppose the steepest descent of of a function f from D in R2 to R at 2 comma 0 is 2, and f is linear in the first coordinate, such that f of 5 comma 0 is 1. Then what is the linear approximation? Okay. So what is the linear approximation LF at 2 comma 0? Okay. So it's not that hard question. It's a simple question. But anyway, so it's an exercise. Try
So
to
using the steepest descent, we can find the grad f. So that we can find, and if is linear in the first coordinate means that we can use this linearity property,
right.
and right. So and we can use this in the linear approximation function using grad f.
Yes. Right. So it is not that hard, but it involves some computation. So yeah, next Thursday we can discuss this, and I will ask what's the answer for that. Okay. So now there is one more thing in the in one variable calculus that we have seen, which is about finding out the maxima and minima. Okay. In particular, the extremum points. For example, in this graph, if you see in the one variable case, if you see this graph, so let me copy this whole thing. Right. So if you see this graph on the left hand side, you see this point. So these 2 points are the points where uh, you achieve a local maxima or a local minima. For example, in the sine x curve, uh, it achieves a local minima at pi by 2 minus pi by 2, and it achieves the local maxima at plus pi by 2. All right. Minus 1 is the local maximum value, minus 1 is the local minimum value. Similarly, the same type of phenomena occur in the higher dimensional case as well. Okay. So there can be points where the function value is the highest among some local neighborhood. Okay. And it is lowest in some local neighborhood. Local neighborhood, what I mean by that, some ball near that point. Okay. So for example, on the figure on the left, on the right hand side, if you see carefully, you will see that there is a point which which attains the maximum value. Okay, if you look at the top of this head, top of this figure, you see there is a point where it hits the maximum value because in the locality it achieves the highest value of the function uh, relative to the other points in that locality. So this is another example of the extreme points. Okay, so the concept of extreme points also makes sense in the high dimension case. All right, so that is what we are going to study. So before that, let me quickly recall uh, the local minima, maxima, uh, or what do we mean by critical point in the one-dimensional case or in one variable case. So let me write now topic. So in one variable, in for one variable functions, let us be a function from some domain in R to R, and yeah, every function in this, then we say a point A in D is a critical point if f is not differentiable at A, or if it is differentiable and its differentiation at A is 0. Okay, so it is called a critical point if it is either differentiable or if it is not differentiable. All right, so these are the two conditions. That's the definition of in one variable case.
Sorry, can you just explain what is this one variable that you keep mentioning even when it is in higher order?
Yeah. So this is not a high dimensional. This is one variable. One variable because it depends on one variable. There is only one variable, one parameter in there. For example, if I look at this function sin x, fx equal to sin x. So this is a one variable function because it only depends on one variable. There is only one variable involved. Whereas if I look at this function, uh, sin x plus y, it is not a one variable function. It is two variable function because it involves two variables. And most importantly, I'm referring to these functions as one variable because of the domain. Look at the domain. Domain is a subset of R. Okay. So R is just a one-dimensional space. That's why I'm calling these functions whose domain is one dimensions are called one variable functions. Functions whose domain is more than one dimension are called the multivariable functions. For example, in this case, the domain is R2, which is a two-dimensional space. So it is called the two-variable. Does that is that fine?
Yeah, but you kept mentioning a one variable even when
But,
you were doing that higher order, right? I don't know, maybe I missed.
right. So that was, yeah, you are correct. But there was some context behind it because I was, for example, in this case, I was saying one can see this one two variable function as one variable. Why? Because my domain, because I've restricted my domain. I'm just looking at the values which varies in this case. So now this vector AV is fixed, this vector U is fixed, only the variable is T. So this two variable function becomes just one variable. So there is some change of variable is happening. So I can convert my two variable function into one variable. For example, the one that I gave earlier. But so, for example, if you look at this function, this is xy equal to sine x plus y. All right. If I try to see R2, so if I just restrict my function for values is restricting the domain of f to uh, x equal to the subset uh, xy to the subset x comma 0. Okay, where x varies in R. If I restrict my uh, function to this subset, so that means what? If I plug in this value, so let's name this subset S. So that means I'm restricted my function to S, and now it becomes just a function from R to R. Because after restricting to S, I need to place y equal to 0. So it will become f restricted to S, it just becomes a function of one variable, so sine x. So if I restrict my function to a particular subset, okay, then it becomes then it need not to be a two variable function. That's what I'm saying. So my restriction earlier was on one dimensional spaces, subspaces of alpha. For example, in this case, I was restricting my function to this line, which is a one dimensional space. All right, this is a line. This is a one dimensional space because it is a linear combination of. It is a affine line, you may say. It is not the uh, yeah, it is a line, but you may say it is not the line that passes through the origin. It is shifted line, and it is one variable because it is t times scalar multiple of one vector. So it is one variable, as we have seen in the Lie algebra. So it is a one variable. Only the variable is t here. There is no other variable. U is constant, and vector U is constant, and vector AB is also fixed. So there is only one variable. So if I restrict to such one-dimensional subspaces of R2, then it only the function varies only on one variable. So it becomes one variable function. So that's what I was mentioning. While calculating the directional derivative, what we do, we restrict our function to a one-dimensional space, subspace, which is defined by the that direction, that vector along which we are performing the directional derivation. Okay, so
Yeah,
that's what I.
got it. Yeah, thank you.
Okay, I hope it makes sense.
Yes.
All right. Um, Coming back to the topic of our discussion, let me rub it all. All right. So, yeah, critical points. So we have seen critical points for sine x curve. There are two critical points in this graph in the domain that I've just mentioned. In this domain, there are two critical points. One is at so yeah. So for example, in the above graph, above graph on left, on the left, there are two critical points of f. Okay, and those two critical points are as one at pi by 2 and the other one is minus pi by 2. All right. Now these two critical points are extremums. Okay, why extremums? Because function takes the local maximum values or relative maximum value or minimum value. Okay, so that's why they are the extreme function, extreme points as well. Okay, so note. So in particular, if you have a function given, every extremum, okay, wherever it takes the extreme value, every extremum is a critical, but not the other way. Critical points may not be extremums other than one-dimensional case, but in higher dimension they not may not to be critical points. So uh, yeah, so let me recall the definition of extremes. Okay, so a point.
Sir, like, could you just come again, like what you said, like critical points are extremas in higher dimension, is it?
Yeah, yeah. No. I'm saying that. So in the above example, okay, so note that pi by 2 and minus pi by 2 are the local extremum points. Okay, there's the first thing to note. The second thing to note is, uh, yeah, local extremum points. In particular, f of pi by 2, which is 1, is a maximum, is a local maximum, and f minus pi by 2, which is minus 1, is a local minimum. All right. So now second point to note is that extreme points, every extremum points is a critical. Okay. However, in higher dimension, in a higher dimensional case, uh, critical point, a critical point need not to be an extremum point.
Okay. You mean like they can be something like point of inflection or something like that, is it?
They can be saddle points. Okay, I
Okay.
will give an example. So,
Okay.
but let me first do it. So this note is important. I will come back to this note once we are done with defining critical points in high dimension. So I will come back to this point. But before that, let me uh, talk about the local extremum points. Okay, for high dimension. So suppose uh, so so local extremums. So let my function f is a multivariable function from d Rn to R, and also assume that there is a point A in D. Okay, so point A in D is called local maxima or minima. So there are multiple names. It is maxima, minima, or maximum, minimum. You may call any of that maxima or minima if for some ball, for some small ball, or some open ball, G containing tilde f of x tilde or for this is for maximum. Okay. For minima, it should be the opposite inequality. It should attain the minimum. For all points x tilde that sits inside the intersection of B and B. All right. So this is the definition of the local maxima and local minima. So for example, let me draw a figure. Okay. So this is a graph of one-dimensional curve, one-dimensional function. Okay, where the x-axis is the below, one is the x-axis, and then you have drawn the graph. Okay. So now if I look at this point, so let's say there are 4 points that you can see as the extremums. All right. So A1, A2, A3, and A4. Now, as you can notice that A1 is a maxima, but it is a maxima up to in some local neighborhood. Okay, if I look at some ball around this point, so it is a nib, sorry, not a ball in this. Okay, 1 minute. So it should be a ball in the domain. So if I look at the small ball in the domain, so this is point A1. Point A1 is not top on the top, it's f of A1. It's f of these points. Okay, so A1 is in the domain. So A1, let's say at A1 it achieves the maximum, but this is not the maximum. Okay, it is a maximum for some small ball around uh, A1. Okay, that's what this means. So it is a maxima value. It takes a maxima around this sum is in the small ball, open ball. Similarly, in A2 also, it is not the minima throughout the domain. It is for some small ball. It is the minima. Okay, that's what it means. But this concept can be generalized in higher dimension as well. So you can think accordingly. Okay, because I have limitation in drawing, so I cannot draw in high dimension, but you can your power of visualization. So I leave it to you. All right. So yeah, now let me state it as a fact. At points of extrema, the gradient, okay, yeah, at a local at a local extrema, A tilde in D, uh, the gradient of f at A tilde is 0 if it exists. Okay, so at extreme points, the gradient is 0 if it exists. If at all exists, then it is 0 at extreme points. Okay, so now we are in situation to define a critical point. Okay, so now the definition of critical points comes. A point A tilde in D is called a critical point of f if, number one, if the gradient exists at A tilde and the point 2, it is 0. Gradient is 0. Okay, so for example, let's consider an example. for better understanding. Consider this function.
Sir, I have a
Yeah.
small question here. So, in the case of a one variable function, so
Yeah,
we
yeah.
considered the critical points for which the f prime a, f is not differentiable,
Right, right.
right? Right. But why is that condition like reversed in case of multivariable functions?
It is not reversed in the case of this. It is just relaxed. We have leaved out one more
Yeah.
condition to define. It is not reversed.
Okay.
Yeah.
So, but grad if exists at a means at a tilde implies that uh, the f is differentiable at a, right?
No,
So only then this
no,
grad f.
no, 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 no. Differentiability existence of grad f does not imply differentiability of it. Yeah. So yeah, I missed out this thing. You are correct. But yeah, but whatever you said, grad f being existence of grad f does not imply the differentiability. Differentiability is much more stronger condition. Grad f exists if all the partial derivative exist. But it may happen that function has all the partial derivative, but it's still not differentiable. For example, you can consider this function xy given by xy divided by x square plus y square and at origin defined by 0. It is 0. So this is at origin. So has this function has the gradient. The gradient of this function exists, but it is not differentiable. All right. And now, and sorry, and let me modify the definition of this. If yeah, so let me modify the definition. This definition is basically it makes sense with the gradient. Yeah, if the gradient does not exist, so we relax the condition to up to the gradient only. We don't need to go up to the differentiability. Gradient does not exist, or gradient of a if it exists, then it has to be 0. Yeah, yeah. So this is the condition.
Yes, sir.
Or if it
That's makes
exists,
sense. Yeah.
yeah, it makes sense, right? Yeah. So earlier I missed out this case. Yeah, if it exists, then it has to be 0. All right. So now, for example, you consider this function xy, f of xy, given by 4 plus x cube plus y cube minus 3xy. So the partial derivative with respect to x. Now we need to find out the all critical points of this function. So how do I find that? So first, I need to calculate the differentiable partial derivative, in particular the gradient of this function. So fx, what is fx? Anyone?
It's just 3x squared minus 3y.
Right. And what is fy? It
It's
is
3y squared minus 3x.
correct. So now, in order to find out the critical point, I need to use this condition because this exists, the gradient exists, so I need to evaluate it equal to 0. All right. So let's do that. So fx equal to 0 and fy equal to 0. This would imply that x square is equal to y and y square is equal to x. So y to the power of y square is equal to y. which would imply that y into y minus cube is equal to 0. Correct? And if I solve this, I would get either y is equal to 0 or y is equal to 1. So if y is equal to 0, x is also equal to 0. And if y is equal to 1, x is also equal to 1. Correct? So I get two critical. All right. Is this example clear to everyone?
Yes.
Yes. So now, coming back to the remark that I made earlier, that not every critical point is a local extremum. Okay. So, especially in higher dimension, particularly. So, it's a local extremum. Local extremum. Okay. So, for example, consider this function f of xy given by minus x square plus y square. Okay. So first, what we will do, we will find out its critical point. Okay. So what are the critical points? For critical points, first we need to do fx. Now, what is fx?
Minus 2.
Minus 2x. And what is fy? Fy is 2y. Now, what are the critical points? Critical point is precisely fx equal to 0, yx, fy equal to 0. So 0, comma 0 is the only critical point. Now, what happens at 0, comma 0? So now the question is whether it's a local. I will prove that it's not a local extrema, because if it's a local extrema, then it needs to be uh, either local minima or local maximum, and it should not depend on along which direction I evaluate the value of the function. Okay, so my claim is that claim f is neither a maxima or minimum. All right. Now, what does this mean? So, in order to prove that it's a maxima, suppose I assume that it's a maxima. So, uh, yeah. So let me draw the xy plane. So this is x and this is y. This is the xy plane. Now, if I walk along, now this is the critical point. 0, 0 is the critical. Now, consider the small ball around it. Okay, consider this ball to be of delta radius. Okay, ball of delta radius centered at origin. So that means this is the delta. So now, where delta is small enough. Now, now if it is a local maxima, that means fx must be greater than f of 0, 0 must be greater than f of x
I think the
for
delta
all.
should be less than 1, right? So delta is less than 0.
Yeah, sorry. Yeah, yeah. Okay, good. Right. So it should be f00 should be, yeah, for maxima it should be larger than all the other effects that is in the ball. All right. Now, what is for maximum? This is for maximum writing. Suppose f is max at 0, 0. So in that case, this is what happens. Now, what is f0, 0? F0, 0 is 0. So my function needs to be either 0 or smaller than 0 for all values of this thing. Now, look at this. I consider two paths. Okay, one path is this, the x-axis. So path 1, my x-axis, and path 2 is the y-axis. So now if I evaluate my function along the path 1, okay, if I evaluate my function path 1, what do I get? I get fx to be, so fx0 is going to be just minus x square. Now, what is minus x square? Minus x square, that means it is function looks like this. It looks like this. Okay. If I draw the graph of this function, suppose this is my z-axis, this is the negative z-axis. So function goes towards the negative z-axis. Okay, it is the maximum at this. But if my function is if I go along the path 2, what do I get? If I move along the path 2, yes, I get y square. Now y square, for y square, it is a what kind of function? It is a minima. So along y-axis, it is a minima. So it contradicts the above inequality, because in this within this ball, it should always be smaller than 0, but I'm achieving the value which is larger than 0. Okay, so it is contradicting this inequality. That means this inequality is not true. That means it is not local maxima. The same argument goes for proving that it is not local minimum. So 0, 0 is a critical point to this function. Okay, but it is neither a maxima nor a minima. So let me write down this. This is, let's say this is A. So, and this is B. This is B1. This is B2. B2 clearly B2 violates violates A. Hence, F hence 0, 0 is not a local maxima. Similarly, 0, 0 is not a minima. So these such points, which is neither a maxima nor a minima, in for two variable functions, it's called a saddle point. Okay. So such points are called, such critical points to be precise. Critical points are called saddle points. All right. Okay. So now we have seen that these maxima make sense for some smaller ball, some smaller neighbor. Okay. Or in some locality. But can we define something which is maxima throughout the domain or something? So for that, we need to restrict our domain. Okay. So we need to define a new type of domain. We need to consider a function which is defined uh, uh, on different type of domain, which is called the closed and bounded domain. So and in those cases, global maxima or absolute maximum always exist. Global or absolute extrema. All right. So let me first define what is a global maxima or minima. So by definition, it makes sense that a point is a global maxima or minima if it attains the maximum value throughout the domain, is absolute or global maxima or minima if fx tilde is smaller than fa tilde for all x tilde in D, or it is larger than fa. So obviously this is for minimum maximum and this is for minimum. And these absolute maxima minima exist for always exist for some particular type of domain which are called closed and bounded domain. Okay. So let me first define what is a closed domain. So global or absolute extremum always exist for continuous function f defined on closed and bounded domain in Rf. Now, what is a closed domain? Closed domain means domain B is said to be closed if it contains all boundary points. And it is said to be bounded if D is contained inside some ball. Okay, contained in some ball. All right. So such for such domains, function always has absolute minimum or maximum. So when we include these type of domains, when we include the boundary points also, and they are bounded also. So how to find maxima and minima in that cases? So how to find, or most precisely, where to find, or how to find absolute max or minima? So for that, one need to look critical points critical points in the interior, or uh, in the points in D. Okay. So for in points in D, all right, points on the boundary, and third, points on the boundary of the boundary. Okay. So in particular, we find critical points inside 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 the domain D, all right, or on the boundary of D, or on the boundary of the boundary of D, boundary of the boundary of. Okay, so let me give you an example of such kind of domain to help you understand this. So, for example, if you consider, okay, so graph of this function, which is x y equal to x square, all right, and this line, which is y is equal to -4, and my domain is precisely the area between these two curves, which is the highlighted part that I just. Okay, so this is my domain. Now, this domain is clearly the uh, for if you want to find out the critical points defined of a function onto this domain, in particular the absolute maxima and minima, then it may exist inside the D, that means the brown part that I've just colored, or on the boundary. The boundary is given by the curves y is equal to x square and y is equal to -4, or the boundary of the boundary, which are the boundary of the boundary are these corner points. One is this minus, uh, yeah, if you place -4, uh, okay, sorry, this is x square minus x square. Yeah, y is equal to minus x square. Right? Yeah. So it is plus -2. So it is 2 -4, -2 -4, 2 comma 2 comma -4. All right. So we will find critical points inside D. That's the first thing. On the boundary, that is y is equal to x square union with y is equal to -4. All right. And boundary of the boundary is going to be these 2 points, plus minus. Okay. We will discuss some examples considering these topics, whatever topics we discussed today. Okay, in the next session, which will be on Thursday. Uh, if you guys have any question, doubts, you can note it down. We will discuss that on Thursday as well. Thursday will be our discussion session. We will discuss many examples. You will see in using GeoGebra how does these pictures looks like. Okay, so yeah, so let's end this today's discussion here. If you have any specific doubt about today's discussion, you may ask now.